We discussed in the previous lesson a way in which vector notation might be employed to effectively find an integer solution to a times x plus b times y is equal to the greatest common divisor of a and b. And in this video, we're going to work through several examples of that technique. Now, we are eventually going to present a flowchart for this procedure, but let's go through it by hand the first time. Let's find integers m and n so that 11 times m plus 13 times n is the GCD of 11 and 13. So I've put 11 as my first number and 13 as my second number. Of course, it doesn't really matter. It's just make a choice and note down what you did, because we're going to represent these numbers as vectors. And remember, the vector notation is the first number times whatever I picked as my first location, the second number times whatever I picked as my second, and then add this up. So this vector 1, 0 is 1 times 11 plus 0 times 13, which is in fact 11. This vector here is 0 times 11 plus 1 times 13, which is indeed 13. So I have a vector notation for 11 and a vector notation for 13. Now what we're going to do is run the Euclidean algorithm to compute the greatest common divisor. And then we're going to go back and look at every time a new number showed up, where did it come from, and how can we compute it as a vector as a linear combination of 11 and 13. So first, let's compute the greatest common divisor. We start with the GCD of 11 and 13. The remainder of 13 over 11 is 2. The remainder of 11 over 2 is 1. The remainder of 2 over 1 is 0. And now that we're looking at the GCD of 0 and something else, the GCD is whatever that other number was. So the greatest common divisor of 11 and 13 is 1, as computed by the Euclidean algorithm. Now what we're going to do is every time a number shows up, find a vector representation. And remember, 11 is 1 times 11 plus 0 times 13, and 13 is 0 times 11 plus 1 times 13. Now in the next line, we got the number 2. Where did the number 2 show up from in the Euclidean algorithm? It was the remainder when 13 was divided by 11, so it's 13 minus some number times 11. And specifically, the remainder of 2 is 13 minus 1 times 11. We have a vector for 13, it's 0, 1. We have a vector for 11, it's 1, 0. So now I have a difference of two vectors, and I can compute that component-wise. 0 minus 1 in the first spot gives me minus 1. 1 minus 0 in the second spot gives me 1. So now I have a vector that represents this remainder of 2, and you can check negative 1 times 11 plus 1 times 13 is in fact 2. In the next line, we get a 1 as our new remainder term, and that was the remainder when 11 was divided by 2. So the remainder 1 must be expressed as 11 minus something times 2. And specifically, it's 11 minus 5 times 2. 11 had the vector 1, 0, and in the previous line, we determined that 2 can be written with the vector negative 1, 1. So I work through component by component. 1 minus 5 times negative 1 is a total of 6. 0 minus 5 times 1 is negative 5. So in each location, we compute these numbers here. Okay? And the next line, the new remainder is 0. But we don't have to find a vector representation for it. We can, it's just not necessary, because we've already computed that the greatest common divisor is 1, and we have a vector to represent 1. So we determined the GCD is 1, and we found a vector for it, but now interpret this vector as what it was supposed to represent. 6 times 11 plus negative 5 times 13. So here is 1 is equal to 11 times something plus 13 times something else, and indeed, the arithmetic checks out. Well, let's take a look at another example. Find integers m and n so that 83m plus 105n is the GCD of 83 and 105. Again, order doesn't really matter, but we have written 83 first and 105 second, so we're going to run the Euclidean algorithm. 83, 105, the first remainder we compute is 22. Now the remainder of 83 over 22 is 17. The remainder of 22 over 17 is 5. 17 over 5 has remainder 2. 5 over 2 has remainder 1. 2 over 1 has remainder 0. And now that we have a GCD computation with a 0 in it, we know that the GCD is just 1. So the Euclidean algorithm has worked its magic, and assuming we can run the division algorithm pretty quickly, has given us our GCD in a relatively small number of steps. Now we start with our vector notation. Okay, a vector is going to represent the first number times 83 plus the second number times 105, just because we put 83 first and 105 second. So 83 I'm going to write as 1 times 83 and 0 times 105. Conversely, 105 is 0 times 83 and 1 times 105. Now we go through all of the steps of the Euclidean algorithm. Each new remainder that was computed, we compute it in terms of these vectors. So the first remainder was 22, which is 105 minus 83. The remainder of 105 over 83, take away 83 once and you get your remainder. 105 had the vector 0, 1, 83 had the vector 1, 0. In each component, we now perform the subtraction. 0 minus 1 gives me minus 1, and in the second component, 1 minus 0 gives me 1. So 22 is this vector, and indeed, this just says 83 times negative 1, and 105 times 1. Hey, there it is, 83 times negative 1 and 105 times 1. So no big surprise so far. Now let's look at our next remainder of 17. This is 83 minus 22 minus 22 minus 22 to finally get my remainder of 17. In other words, it's 83 minus 3 times 22. So 83 had the vector 1, 0. 22 we just computed had the vector negative 1, 1. So now let's go ahead and compute in each coordinate. 1 minus 3 times negative 1 is equal to 4. 0 minus 3 times 1 is equal to minus 3. And remember that this corresponds to saying 83 times the first number plus 105 times the second. And you can check that this is indeed 17, but the vector notation is a very, very handy way of keeping track of this. In the next line, we have 5 as the remainder of 22 over 17. That's just 22 minus 17. We already had a vector for 22, and we just computed a vector for 17, so take their difference. Negative 1 minus 4 is negative 5. 1 minus negative 3 is positive 4. So here is a vector to represent 5. And it's not necessary to write, but we could state that this means 5 is equal to 83 times negative 5 plus 105 times 4. And you can check, indeed, that does work out. In the next line, our remainder is 2. That's 17 minus 5 3 times. So 2 is 17 minus 5 3 times. 17 we computed to be 4 comma negative 3. 5 we computed to be negative 5 comma 4. Now let's go coordinate by coordinate. 4 minus 3 times negative 5 is 19. Negative 3 minus 3 times 4 is negative 15. Next line, the remainder of 1 was 5 minus 2 times 2. Here's the vector for 5. Here's the vector for 2. Negative 5 minus 2 times 19 is negative 43. 4 minus 2 times negative 15 is positive 34. And we are done. The GCD is 1. And we now have a vector that represents 1. So we found the GCD was 1, and this vector tells me that the GCD, 1, can be written as 83 times negative 43 times 105 times 34. And that does, in fact, check out. Now, at the very beginning, if you stopped running the Euclidean algorithm here, and you say, great, now I know the GCD is 1, let's try guess and check. 83 times 2 is 166. Well, if I take away 105, that's still too big, and if I take it away twice, that's too small. Maybe 83 times 5, that's like 400 and something. So let's take away 4 of those. No, that doesn't quite work either. Guess and check was going to take a really long time to get you to one of the answers of 83 times negative 43 and 105 times 34. So getting accustomed to running this sequence of steps is, trust me, incredibly much faster than trying to do this by guess and check. Learn how to work with these vectors, and you will save yourself so much frustration and time on working through these extended Euclidean algorithm problems. Well, we promised a flowchart algorithm, and here it's going to be. So first, what we're going to do, we're simultaneously going to find the GCD of the two numbers, but then we're also going to find a vector representation, m comma n, so that am plus bn is equal to the GCD. So rather than run the GCD algorithm and then go back, we're just going to do both of them simultaneously. Here's the flowchart. I just want to point out we're being a little sloppy in these boxes because we're doing lots of computation at once. This was a requirement to make it fit reasonably on the page. Okay, just do all of these computations first and then replace the things over here. This is important because, for example, this line actually changes the value of x, but I don't want to use the new value of w and x here. So do all of these computations and then replace all of these at once. Don't just do them in order. Do all 4 of them at once. Okay, it's not the best practice to write things like that, but in order to make it fit on the page, it was kind of necessary. So as the algorithm runs, okay, we're keeping track of a bunch of different things. So on the one hand, we're going to be computing the GCD of the numbers a prime, b prime, which start as just a comma b. If the first number is 0, then I'm trying to compute the GCD of 0 and something, so I should just output the other number. Okay, that's my GCD. Suppose a prime isn't 0. Well, these things here are going to affect my q and my r, so let's leave that aside. Here we do our standard Euclidean algorithm. The first number moves into the second slot, and the remainder up here moves into the first slot. So these computations with this one up here are my standard Euclidean algorithm. Compute the remainder, put it in the first slot, and shift the other number over into the second one. So here's how a prime and b prime are just the Euclidean algorithm keeping track of the 2 numbers that we're computing the GCD of. Now, a prime is going to be represented by the vector wx. B prime is going to be represented by the vector yz, apologies. So a prime begins at a. Wx begins as 1, 0. So indeed, 1 times a plus 0 times b. On the other hand, y times z starts as 0 times a plus 1 times b. So the vector yz does in fact start off keeping track of b prime. Having computed q and r, this step here says this new wx computes the vector representation of my new remainder that I have computed, whereas the old vector now gets shifted over to be the vector of the second component, because what was in the first location moves over to the second. So the vector that used to keep track of the first location now keeps track of the second. The first location is now this remainder here, which is computed according to this computation right here in terms of the old vectors. So here's the algorithm written all small so that we can try to execute. Find m and n so that 15m plus 28n is the GCD. All right, so we start. We input a and b and check, yes, b was not 0. Now we declare a whole bunch of things. W, x, y, z, q, r, a prime, b prime. W is 1, x is 0, y is 0, z is 1, q is 0, r is 0, a prime is 15, b prime is 28. This just starts as your values of a and b. Now I come up and I ask, is a prime 0? No, 15 is not 0. So I have to come and do these computations here. B prime is 28, A prime is 15. So the first quotient, 28 over 15, is going to be 1, whereas the remainder is going to be 13. So I store 1 into the value of Q, and I store 13 into the value of R. Now I do all of these computations and store them all. Okay, so A prime gets put in as B prime, so 15 is now B prime, and the remainder is A prime, 13. Then I compute this vector right here, y minus qw. So far, y was 0, q was 0. Sorry, q was 1. We replaced it here. So y is 0, q is 1, and w is 1, for a net result of -1. Z minus qx, z is 1, q is 1, x is 0, so that's a 1. So this is now what I'm going to store as wx. But what I currently had as wx 1, 0 gets stored as yz. Next, I come back and I check a prime has now gotten a new value. It was that remainder of 13, but 13 is still not equal to 0. So b prime is now 15. A prime is now 13, so I'm going to compute this quotient and this remainder. So the new quotient is 1 and the new remainder is 2. So I store 13 as b prime. That was my old value of a prime right here, and that remainder gets stored as a prime. Now I need to compute these two vectors. So first, y minus qw. Well, the current value of y is the first entry of this vector, that's 1, minus q was just computed to be 1, times w was the first entry of this vector, which was minus 1. So I end up with a 2. In the second component, I'm computing z minus qx. Z was previously computed as the second entry of this vector, so that's 0. Minus q was computed to be 1. X was the second entry of this vector, which was 1. So overall, that works out to be minus 1. So wx is going to be stored as 2 comma minus 1, but first let's take our old value of wx and store it as yz. All right, now I have a prime is 2, but I'm checking again, is that 0? No, it's not. So now I need to do another quotient and remainder, another step of the Euclidean algorithm. B prime is now 13 and a prime is now 2. So the quotient is going to be 6 and the remainder is going to be 1. I take that old value of a and store it as b, and I take my remainder and I store it as a. Then I need to compute all of these new vectors, store them as wx, and take my old value of wx and store it as yz. Then I come back and I check a prime is not in fact 0 yet, so I need to do this again and compute new vectors. There they are. But now I have a prime is 0. So the first thing I output is the GCD, b prime, which was most recently computed here. So the GCD is going to be output as 1. The second output is going to be the vector yz, which is negative 13, 7. So first we output 1 as the GCD, and then we output negative 13, 7 as the pair m, n. And indeed, 15 times negative 13 plus 28 times 7 is indeed equal to the GCD, which is 1. Okay, so this is not the most convenient flowchart to follow, but it does capture the process. So let's look at another example. Find all the solutions xy so that 15x plus 28y equals 1. Now you may have kind of groaned and said, oh, we're going to have to do all that work again. No, we actually already found one solution. We found that 15 times negative 13 plus 28 times 7 does equal 1. And this problem, we're supposed to find all solutions. But remember, if you know one solution, then all solutions are given by a pretty convenient formula. X is the one x value you found, negative 13, plus the other number, 28, times an arbitrary integer over the GCD of 15 and 28. But we already computed this GCD to be 1. So x will be given by 13 plus 28k, and similarly, y will be given by 7 minus 15k. So if we were trying to find all x and y that solve it, here they are. X has to be of this form, and y has to be of this form. Another example we could do is not just find all solutions xy, but find the solution xy that makes 15x plus 28y equal to 1 and makes the absolute value of 2x plus 3y as small as possible. Now we've already found all solutions up here. Therefore, 2x plus 3y must be 2 times this plus 3 times that, 47 plus 11k, once you simplify all of this down. So any solution xy must be of the form x is 13 plus 28k and y is 7 minus 15 times k, where these two k's are the same integer. Therefore, 2x plus 3y must be given by 47 plus 11k. K can be any integer, and our goal is to make this absolute value as small as possible. How do I make the absolute value of something as small as possible? I make the thing I'm taking the absolute value of close to 0. So how can I make 47 plus 11k as close to 0 as possible? It becomes fairly obvious that you want k to be negative. Well, if k is negative 4, I end up with a 3, but if k is negative 5, I end up with an 8. If I made k more and more negative, 2x plus 3y, 47 plus 11k, would become more and more negative. The absolute value would merely continue to grow. If x was larger than negative 4, this would just be a larger positive number. So the value of k that makes this as close to 0 as possible is k equals minus 4. Therefore, k equals -4 is going to give me the x and the y that solve this question. So since k is -4, I can come back here and solve for x and y. X is -99, y is 67. That is a pair of numbers, x and y, so that 15x plus 28y equals 1, but furthermore, the absolute value of 2x plus 3y is as small as it could possibly be. So let's talk about the technique we just developed. So the flowchart algorithm, it's nice to have, and if you really wanted to program it, go ahead. Be careful about that step where I said we were being a little wishy-washy about what order we did computations in. You can get around that by storing the two vectors as a quadruple of number and moving them around in kind of a clever way. But most people don't actually use the flowchart algorithm. They just get accustomed to the way we did the first two examples, the by hand method. You can do whatever you want, but I do suggest making sure it makes sense and that you can execute it with few, if any, errors. Okay? Just pick random numbers, 2 or even 3-digit numbers, and then try to run that procedure to solve finding integers m and n so that am plus bn is the GCD. Check your results with a calculator or computer, but try to work by hand as much as possible. I would conservatively estimate it that once you've done this accurately and fairly quickly about 20 times, it will become a boring and totally uninteresting problem to do. And that's the best feeling to have when it comes to these computational sorts of problems. Anytime a problem in a math class says compute this, or asks you to find numbers that satisfy some sort of equation and you know you're just going to be doing a bunch of boring computation, you want to have practiced it enough that you're sure you can do it without making mistakes and you can do it quickly. And it takes a lot of practice, and you might, make some mistakes at the beginning, but practice it and get to the point where you're just like, fine, if someone asks me to do this, I'll roll my eyes. I'll be prepared to be a bit bored for 5 minutes or so, but I know I'm going to be able to get to the correct answer because I've done this so many times. That's the level of just competence and proficiency that you want to reach with this sort of problem.